This is the last lesson in the Class A Performance section. This lesson will focus on the Class A performance requirements for the landing stage of flight. There are two main regulation requirements. The first requirement is that the landing distance must not exceed the landing distance available. In other words, the aeroplane must be able to land within the length of the runway. This requirement can be called the landing distance requirement. Remember that the landing starts at the 50-foot landing screen and ends once the aeroplane has reached a full stop. Don't forget that the target speed to be attained at the screen height is called VREF, which you may recall for a Class A aeroplane must be no less than 1.23 VSRO and no less than VMCL. The second requirement is that should the aeroplane be unable to land, it must be able to climb away from the aerodrome with an adequate climb gradient. This latter requirement can be called the landing climb requirement. We will deal with the climb gradient requirements first. The climb gradient requirements are a little complicated and are spread through both JAROPS 1 and CS25. Assimilating both these documents allows the landing climb gradient requirements to be split into two parts. The two parts are based on either all engines operating or with one engine inoperative. The all engines operating landing climb requirement is sometimes called the landing climb. This requirement is intended to guarantee adequate performance to arrest the descent and allow a go-around from the final stage of a landing. The regulations state that the steady gradient of climb may not be less than 3.2%, with both engines operating, but only using the amount of thrust that is available after 8 seconds on initiation of go-around power. The speed used in the climb cannot be less than either 1.08 VSR for 4-engine aeroplanes or 1.13 VSR for all other aeroplanes, and a speed not less than VMCL and not greater than VREF. The second part of the climb requirement is based on one engine being inoperative and is sometimes called the approach climb. This requirement is intended to guarantee adequate performance in the go-around configuration after an approach with an inoperative engine. The regulations state that the steady gradient of climb may not be less than 2.1%, with the critical engine inoperative and the remaining engine at go-around power. The mass is assumed to be maximum landing mass, and the speed used in the climb cannot be more than 1.4 VSR. Lastly, the landing gear is assumed to be retracted. However, the approach climb gradient requirement does change. For 3-engine aeroplanes, the gradient must not be less than 2.4%, and for 4-engine aeroplanes, the gradient must not be less than 2.7%. Note that the gradient requirements stipulated here are all air gradients, and therefore are independent of wind. JAROPS 1 more precisely describes the climb requirements by stating that the landing mass of the aeroplane must be such that the climb gradient requirements can be met. The maximum mass that the aeroplane can have and still meet the climb gradient requirements is called the landing climb limit mass or climb limit landing mass. Exceeding this mass means that the aeroplane will not be able to attain the climb gradient requirements. Shown on page 47 of section 4 in cap 698 is an example of a graph to calculate the landing climb limit mass. Working through an example, we can assume a temperature of 20 degrees Celsius at a destination airfield pressure altitude of 2,000 feet. The flap setting section here determines how far up the sloping guideline we go. In our example, we'll assume a flap setting of 40 degrees, which means we go straight through the flap section. In this example, the landing climb limit mass is 61,800 kilograms. Remember, exceeding this mass would mean it would not be possible to meet the climb gradient requirements. Before we complete the study of the graph, ensure you have looked at the correction information. Notice that near the bottom of the page is a long list of corrections that may need to be applied. The graph is based on the air conditioning packs being on automatic. If the air conditioning packs are off, increase the landing climb mass by these amounts depending on the flap setting. The bottom set of corrections apply to in-flight icing conditions and the use of anti-ice equipment. Since this equipment drains thrust from the engines, the landing climb limit mass will need to be corrected. This completes the graph for working out the landing climb limit mass. But remember, not all Class A aeroplanes have graphs that look like this, so be sure to familiarize yourself with the performance data of the aeroplane type you fly. Having discussed the landing climb requirements, let us now turn to the landing distance requirements. JAR Ops 1 states that an operator must ensure that the landing mass of the aeroplane allows a full stop landing from 50 feet above the threshold within 60% of the landing distance available for turbojets and within 70% of the landing distance available for turboprops. This means that turbopropeller aeroplanes must be able to land within 70% of the landing distance available, but jet aeroplanes must land within 60% of the landing distance available. To help you calculate the relevant distance, use the factor 1.43 for turboprops and 1.67 for turbojets. Let's work through a few examples so you can become familiar in using them. A turboprop aeroplane has a calculated landing distance of 693 meters. What is the minimum length of landing distance that must be available at the airfield in order to comply with the regulations? In other words, we must work out what 693 meters is 70% of. Therefore, multiply 693 meters by 1.43. This gives an answer of 991 meters. Therefore, if the runway is 991 meters or more, the aeroplane is landing within 70% of it. Let's look at it another way. If the available landing distance was 2015 meters, then what must be the maximum landing distance of a turboprop in order to comply with the regulations? In this case, we must find out what 70% of 2015 meters is. Therefore, divide 2015 meters by 1.43. This gives an answer of 1,409 meters. In this example, a turboprop aeroplane must come to a full stop within 1,409 meters. Let us carry out one more example, but this time using a turbojet aeroplane. Remember, turbojets must land within 60% of the runway, and the factor to use is 1.67. If the calculated landing distance is 857 meters, what is the minimum length of landing distance available? For this example, multiply 857 by 1.67. This gives an answer of 1,431 meters. Therefore, the landing distance available must be more than 1,431 meters long. These examples are important, since questions like this form part of the aircraft performance exam. Try not to get confused about when to multiply or divide by the factor.